Now let's look at how we can actually evaluate and compute cross products. Cross products for unit vectors can be written as I hat cross j hat, which is the same thing as negative j hat cross I hat, which is equal to the orthogonal unit vector k hat. J hat cross k hat is equal to the negative of k hat cross j hat, which is equal to the orthogonal unit vector I hat. K hat cross I hat is equal to the negative of I hat cross k hat, which is equal to j hat. I hat cross I hat, j hat cross j hat, and k hat cross k hat are all equal to the zero vector. Now all we need is a way to compute the actual components of a cross product. So let's let u be u sub 1 I hat plus u sub 2 j hat plus u sub 3 k hat, and let's let v be v sub 1 I hat plus v sub 2 j hat plus v sub 3 k hat. U cross v is equal to u sub 1 I hat plus u sub 2 j hat plus u sub 3 k hat cross v sub 1 I hat plus v sub 2 j hat plus v sub 3 k hat. We're going to use the distributive property here. I'm going to get u sub 1 v sub 1 times I hat cross I hat plus u sub 1 v sub 2 times I hat cross j hat plus u sub 1 v sub 3 times I hat cross k hat plus u sub 2 v sub 1 times j hat cross I hat plus u sub 2 v sub 2 times j hat cross j hat plus u sub 2 v sub 3 times j hat cross k hat plus u sub 3 v sub 1 times k hat plus I hat plus u sub 3 v sub 2 times k hat cross j hat plus u sub 3 v sub 3 times k hat cross k hat. But whenever I cross a vector with itself, it is equal to 0. So the I hat cross I hat term is 0, the j hat cross j hat term is 0, and the k hat cross k hat term is 0. So for the cross product of u and v, I'm left with u sub 1 v sub 1 times I hat cross j hat plus u sub 1 v sub 3 times I hat cross k hat plus u sub 2 v sub 1 times j hat cross I hat plus u sub 2 v sub 3 times j hat cross k hat plus u sub 3 v sub 1 times k hat cross I hat plus u sub 3 v sub 2 times k hat cross j hat. I hat cross j hat is k hat, I hat cross k hat is negative j hat, j hat cross I hat is negative k hat, j hat cross k hat is I hat, k hat cross I hat is j hat, and k hat cross j hat is negative I hat. So that means that u cross v is equal to u sub 2 v sub 3 minus u sub 3 v sub 2 I hat plus u sub 3 v sub 1 minus u sub 1 v sub 3 j hat plus u sub 1 v sub 2 minus u sub 2 v sub 1 k hat. Now before you work up a big sweat trying to memorize all of this or write it on your note sheet, let's take another look. Let's construct a 3x3 matrix with the unit vectors across row 1 and the components for u in row 2 and the components for v in row 3. The determinant of this matrix can be computed by a method of diagonals or by expanding about the first row. I find the method of diagonals to be easier, so that's what I'm going to do. I'm going to write the determinant for my matrix with the unit vectors in the first row, the components of u in the second, the components of v in the third, and then I'm going to copy column 1 and column 2 to the right, multiplying along the diagonal from I hat down to the right. I get u sub 2 v sub 3 I hat. Then I add the product along the second diagonal from j hat to the right, u sub 3 v sub 1 j hat. And then I add the third diagonal, u sub 1 v sub 2 k hat. Then I subtract the sum of the products of the off diagonals starting with k hat. The product from k hat down to the left gives me u sub 2 v sub 1 k hat, and I add u sub 3 v sub 2 I hat and u sub 1 v sub 3 j hat. My determinant becomes the quantity u sub 2 v sub 3 minus u sub 3 v sub 2 I hat plus the quantity u sub 3 v sub 1 minus u sub 1 v sub 3 j hat plus the quantity u sub 1 v sub 2 minus u sub 2 v sub 1 k hat. This is the cross product of u and v. In other words, the cross product is just the determinant of a 3 by 3 matrix that is populated with unit vectors in row 1 and the components of the u and v vectors in rows 2 and 3 respectively. Let's work an example. I want to find the area of the triangle with vertices located at the point A given by coordinates 1, 2, 3, the point B with coordinates 5, 1, 5, and the point C with coordinates 2, 3, 3. First, I'm going to set up a coordinate system in R3 and plot my points A, B, and C. A is at the coordinates 1, 2, 3, B is at coordinates 5, 1, 5, and C is at coordinates 2, 3, 3. I can construct a triangle by connecting each of these points as vertices for my triangle. The line segment from A to B can also be written as a vector AB. The vector AB has the vector component form 4i hat minus j hat plus 2k hat. The vector from A to C has the vector component form I hat plus j hat. The area of the triangle is half the area of a parallelogram. So if I construct another triangle that forms the other half of a parallelogram with side lengths AB and AC, I know that the area of a parallelogram is the magnitude of the cross product of the vector AB cross AC. So I'm going to construct the cross product of the vector AB and AC by computing the determinant of a 3 by 3 matrix with the first row populated with I hat, j hat, k hat, the second row populated with 4, minus 1, 2, and the third row populated by 1, 1, 0. Using an alternative form for cross products of expanding about the first row, I'm going to get a cross product that's equal to the determinant of a 2 by 2 matrix, negative 1, 2, 1, 0, times I hat, minus the determinant of a 2 by 2 matrix, 4, 2, 1, 0, times j hat, plus the determinant of a 2 by 2 matrix, 4, negative 1, 1, 1, k hat. This gives me the vector negative 2 I hat plus 2 j hat plus 5 k hat. The magnitude of this cross product is given by the square root of 4 plus 4 plus 25, which is the square root of 33. This is the area of the parallelogram. The area of the triangle is 1/2 this magnitude, the square root of 33 over 2. Let's work another example. I want to find a vector normal to the two vectors given in component form by 1, 2, 3 and negative 2, 4, negative 1. We know that the vector obtained from a cross product will be normal to both vectors used in the cross product. So all I have to do is compute this cross product. In other words, I need to take the vector 1, 2, 3 and cross it with the vector negative 2, 4, negative 1. I'm going to set up the determinant of my matrix populated with I hat, j hat, k hat, 1, 2, 3, negative 2, 4, negative 1. Expanding about the first row gives me the determinant of the 2 by 2 matrix 2, 3, 4, negative 1 times I hat minus the determinant of a 2 by 2 matrix 1, 3, negative 2, negative 1 j hat plus the determinant of a 2 by 2 matrix 1, 2, negative 2, 4 k hat. This gives me the vector negative 14 I hat minus 5 j hat plus 8 k hat. In component form, this is just written in angle brackets as negative 14, negative 5, 8. This is the vector that is orthogonal or normal to the two given vectors 1, 2, 3 and negative 2, 4, negative 1. Now you get to try it. Pause the video and compute the cross products of u cross v and v cross u. If the vector u is given by the components 3, negative 4, 6, and the vector v is given by the components 1, 2, negative 1. When you're ready, restart the video to check your understanding. In order to compute the cross products of u cross v, I'm going to construct the determinant of a matrix with the first row populated by the unit vectors I hat, j hat, k hat, the second row populated by 3, negative 4, 6, and the third row populated by 1, 2, negative 1. I will expand about the first row in my matrix so that my cross product is given by the determinant of a 2 by 2 matrix negative 4, 6, 2, negative 1 times I hat minus the determinant of the 2 by 2 matrix, 3, 6, 1, negative 1 times j hat, plus the determinant of the 2 by 2 matrix, 3, negative 4, 1, 2 times k hat. This gives me the vector negative 8 I hat plus 9 j hat plus 10 k hat, or in component form, the vector negative 8, 9, and 10. To compute the cross product V cross U, I once again construct the determinant of a matrix using these two vectors. The first row is populated with I hat, j hat, k hat. The second row is populated with 1, 2, negative 1. The third row is populated with 3, negative 4, 6. Expanding about the first row, I get the determinant of a 2 by 2 matrix, 2, negative 1, negative 4, 6 times I hat, minus the determinant of a 2 by 2 matrix, 1, negative 1, 3, 6 times j hat, plus the determinant of a 2 by 2 matrix, 1, 2, 3, negative 4 times k hat. This gives me the vector 8 I hat minus 9 j hat minus 10 k hat, which is equal to the vector in component form 8, negative 9, negative 10. This is how I compute cross products. I set up a matrix and either expand about the first row, or I use the method of diagonals to compute the determinant, which will give me the cross product of two vectors in R3. Be sure and let me know if you have any questions about computing cross products.